In this video, we're going to be talking about some complex projectile math. So please try to keep up, please take notes, and I'm sure you will be fine. Okay, so let's say I have an object that I decide that I'm going to launch at some angle. Okay, well, what we know is that we can break apart its velocity into its x and its y components. So it will have some horizontal component and it will have some vertical component. Now the only component of this object's velocity that's going to change is the vertical component. Remember that the horizontal component of the velocity stays constant. There's nothing pushing on the in the horizontal direction after it's let go, versus in the vertical direction where gravity is constantly pulling it down and slowing it down. So then what happens is that this object ends up having a trajectory that follows, something that kind of looks like that. All right, and then on the other side, right before it hits the ground, it has again some velocity. Now that velocity again can be broken up into the horizontal component and the vertical component. And what you'll find, if this is drawn, more reasonably and better, what you'll find is, well, you can find the range here. If we go from here to here, we can find the maximum height. Okay, and we can find all of those things, by using vector analysis, using how long does it take to go up, how long does it take to come down, etc., etc., etc. Okay, now there is one other thing here. Okay, the velocity in the vertical direction that this object goes up will be the same as the velocity in the vertical direction that this object comes down. It'll just be in the opposite direction. So here's what I mean. All right, the velocity in the initial velocity in the vertical direction will be equal to the final velocity in the vertical direction. It'll just be in the opposite direction. Okay, we could look at that by say you have a ball and you throw it up and it comes down. It will come down and be at the exact same spot that it was. When it's at the exact same spot that it was, it will be moving just as fast as when you threw it up, but in the opposite direction. Okay, so this is something that we can say. Now, we can also say that if we want to calculate the time of flight, or how long this projectile is in the air, we could use, if we know the final velocity and the initial velocity, we could use the equation, the final velocity in the vertical direction is equal to the initial velocity in the vertical direction plus at. Now, what I'm going to do is I'm going to say minus the acceleration due to gravity times t. And that's the same thing as saying the acceleration is equal to negative 9.81 meters per second squared. That's what I'm taking into account here. Now, I can say that the final velocity in the y direction is the same as the initial velocity in the y direction. So then I can rewrite this and say that negative VIY is equal to, well, VIY minus the acceleration due to gravity times the time of flight, how long this object is in the air. Okay? Now, if I do some rearranging here, I would get, I'd add VIY to both sides, add VIY, I get negative 2 VIY equals negative GTF. So I'm solving this for the time of flight. I can figure out that the time of flight is equal to 2 VIY over the acceleration due to gravity. Now, that's all well and good, but I have a vector here that's not in the y direction. So then what I can do is I can say, well, I remember that the initial velocity in the y direction is going to be whatever the initial velocity is, this would be my initial velocity, times the sine of whatever angle I'm launching at. So then I can take that and plug that into here. And what I get is a time of flight equation. And that means that my time of flight is equal to 2 times the initial velocity times the sine of the angle that it's launched at divided by the acceleration due to gravity. And that will tell me how long my object is in the air from when I start to when I end. Now, we can also do it the other way that we did it, where we find it going up, and then we just multiply it by 2. But notice that this is the exact same thing. Vy, which is vi sine theta, divided by g, now I'm just multiplying it times 2. Okay. Now, there is one other thing and one other derived equation that I want us to look at, and that is the equation for range. So what I'm going to do is I'm just going to kind of erase this stuff that we have here so that we can talk about range. Now, when I'm talking about the range that an object is traveling, I'm talking about its horizontal displacement from start to finish. And if you remember, we said that you can find that horizontal range by taking the velocity in the horizontal direction times the total time. So total time. Now, total time in this case is going to be the same thing as the time of flight. Rock on. Now, we also know that the velocity in the x direction is going to be whatever my initial launch velocity is times the cosine of the angle that I'm launching at. So I'm going to have a big messed up thing. But let's check it out. All right? My range then is equal to VI cosine theta times my total time, which is 2 VI sine theta over G. Okay? Now I can combine some things because I have some things that are the same and I'm multiplying these two by each other. And when you're multiplying fractions, you multiply numerator, numerator, denominator, denominator. So I can pretend like this is over 1 and say now that my range is equal to, well, I'm going to move this 2 and that 2 is going to be first. Okay? Then I have VI times VI, which is going to be VI squared. And then sine theta, and then cosine theta. It could be either way. Okay? Divided by 1 times G, which is just G. Okay? Now, what's going to happen here is that sine theta cosine theta is actually a trigonometric function. And what that means is that it equals something else mathematically. So I'm just going to plug that in here. So my horizontal range then is going to equal 2 times VI squared times sine of 2 times my angle over G. And that will give me my horizontal range. Now remember, that's all derived from how the velocity in the x direction and the total time. That's just a derivation. I can still do it the other way and it's still fine. However, I do want you to keep these equations in mind because they may be helpful at some point in time. I'm not going to ask you to memorize them. I may ask you to use them because they can be useful and they do make your time go a little bit faster instead of going through the whole problem-solving process. But I want you to be able to do both sides of it. So make sure that you understand what's happening here and what's happening in the other video.